Ladies and gentlemen, welcome to video number 28 in a series of video lectures that are companions to the book The Fivefold Sun, which was filed at the Bibliothèque Nationale de France in Paris in late 2017. This book encompasses 15 volumes, and we have on all 30 videos to cover this material. We are now on December the 12th in the year 2018, about a year later. Today we deal again with the solar surface, and we start addressing the issue of the spatial distribution of sunspots. In this video we will first tackle the problem of estimating the total number of physical sunspots and sunspot groups at the peak of the solar cycle at the solar surface. In this video, we start with an introduction to this topic and then go back to the issue of whether there are 60 bipoles at the surface of the Sun at the peak of the cycle. The introduction is for the last leg of our series of videos of our journey through the Sun, following the book The Fivefold Sun. We started from the core of the solar ball in video 10 and arrived in the past two videos at the solar surface. So we went from the Sun's center outward and followed a path which is exactly inverse of a geocentric point of view, in which the Sun is fathomed from the Earth. We are now at the solar surface, and we started in the last two videos with the cells, the surface cells at the photosphere, and now we start dealing with activity markers at the photosphere, which are the sunspots. So the final point in the final Fivefold Sun project is what was first sighted in the Sun, the sunspots, by Harriot, who in 1610 was the first person who was able to enumerate individual sunspots, to count them. We started from the center, from the energy-generating core, which is the least well-known, and we end with the best-known, the surface. Eugene Parker, in 2008, wrote this important remark about these sunspots. They are well known to observers for many centuries, now 4 centuries, possessing fascinating internal fine structure and still not understood. So Parker asked, why is the Sun compelled by basic laws of physics to form sunspots after all? Here we are not in a physical investigation. We rather are interested in a numerical and a kinematic approach of the Sun and its cycle, and we will in the following try to arrive at hints of what might compel the Sun to create sunspots from a more mathematical and then geometrical approach. In part 6 of the Fivefold Sun as a book, section B is devoted to the distribution of sunspot groups, sunspots, and magnetic bipoles at the solar surface. Of course, this can be assessed only during peak activity. Otherwise, there are in the minimum epoch no such features, and in the intermediate epochs, numbers which are not characteristic of the extrema that we expect. In section 7, we investigate in the book the numerical sunspot distribution, and this will be the topic of this video, except the spread of the numbers of sunspots among the several sunspot groups, which we dealt with in the next video. We go back to part 1 of the Fivefold Sun, and to video 6 in this series, in which we arrived at the conclusion that over the 144 rigid rotations of a characteristic quasi-decadal cycle length, the equator laps the pole 60 times, so that there are 60 turns of magnetic field lines just below the solar surface across the solar hemisphere of the solar globe. Then it was postulated or conjectured that for these 60 laps emerged 60 bipoles, and this idea stems from the Babcock model of 1964, which is still largely regarded as a valid model. Now in part 6, we want to count the actual sunspots and figure whether there are 60 bipoles or not at the peak of the solar cycle in the hemisphere of the Sun. We want to count physical sunspots and sunspot groups individually and arrive at absolute numbers. This is opposed to what we did in the previous entire project, in which we relied on synthetic statistical indices for the sunspot number, which in fact is often in solar physics parlance not a sunspot number, but either the relative sunspot number or the group sunspot number. The relative sunspot number is a combination of count of sunspots and counts of sunspot groups, and the group sunspot number is a number of groups but multiplied by an arbitrary number of spots per group. Now we want actually seen physical sunspots and groups in drawings directly from observatories. In chapter 1 of section 7 in part 6, we introduce the retained methodology for this determination. The epoch is the peak rotation of the cycle. This is straightforward. Then we will discuss how to go around the lack of a firm basis for the determination of absolute physical numbers of sunspots. We will see whether there is, after all, such a thing as a true absolute number of sunspots, propose a methodology to track this number, and we will state that we retain as a source station for these direct statistic the drawings from the Kanzelhöhe Observatory in Austria. We'll see why. Of course, we use also other observatories, and you see which ones. There is no firm basis in the literature for actual absolute numbers of sunspots. First of all, for the groups, there is no systematic consistency in publications. There are competing classifications for sunspots and sunspots per group. We do not have an accepted quantity in the literature because this number, this quantity, is not regarded as a realistic endeavor. So there is a lack of extant data sets and a lack of definitions, and this special case at the end of this project, for the first time we had to create the data sets and the definitions, and no meta-analysis per se can be performed. Before we go further into the methodology, let us ask ourselves the question: if the data sets, the definitions do not yet exist, is it not futile to try to build them? After all, if experts did not pursue this endeavor, maybe they have a very good reason. As we shall see now, it is yet possible to try. First of all, is there such a notion as a true absolute number for sunspots at the photospheric surface? We saw that the published sunspot numbers are in general not actual absolute counts, yet sunspots, it is clear, it is accepted that they are not a fractal phenomenon, so it is not in their substance something that it is a fallacy to try to count. They are also not so short-lived that any count would fail to reflect them. There are, if you follow the objections, no major physical objection to the fact that there is a physical existence of a true total number of sunspots. Maybe it is just a question of knowing how to approach this true unknown quantity. One of the main technical issues among experts is whether an instrument, an observatory spacecraft, which is able to see best, will not include in a count of sunspot things that are in fact only pores, or even smalling dots which physically are not sunspots. This is a major controversy. Then another controversy is whether, because of incontrovertible perturbation from the Earth's atmosphere, the count of sunspots at Earth would in any case be a count by default missing some spots. But now that there are some spacecrafts that see spots in the outer space, from the outer space, we know how to calibrate this. And in fact, we will see that at Earth it is possible to match the precision of the spacecrafts if the observatory is not in an urban region, is at a very high altitude, and is right above a lake. And we have just one station in this case in point, the Kanzelhöhe Observatory in Austria. The retained methodology for the tracking of this true absolute number of sunspots is to go after the number of magnetic bipoles, the physical entity that we retain as relevant. And we will arrive to approach this through the notion of an equivalent magnetic dipole, which is merely the number of sunspots divided by 2. Then we will define the targeted accuracy level for the sunspot count, and it is to assess it directly from the drawings by the observing station with the highest sunspot count on record. This is the Kanzelhöhe Austrian Observatory. Then we have two calibration issues, because there will be days or rotations in which seeing conditions will be different, and there will be observations in cycles which, because of their length, short or long, are bound to have more or less sunspots than average. So we will calibrate according to seeing conditions and to cycle length. So we will arrive at a number of sunspots from Kanzelhöhe's archive. We'll arrive at a number of bipoles from this number of sunspots, and we will arrive at a number of groups. Of course, this is in each case per solar hemisphere. First, we start with the number of sunspots. The number of sunspots on the solar disk during the peak rotation is as follows from Kanzelhöhe archive. The median during the single peak rotation at maximum epoch is found to be about 118. If we calibrate then as a function of seeing conditions, we find more, we find 123. And then if we calibrate as a function of solar cycle length, we go back to about 118. So in conclusion, we go back to the initial raw estimate of 118, 118.4 plus or minus 1.5 for the median number of sunspots for the peak solar rotation. This table gives the source data. You see that in this database from the archive of Council, we have all the cycles since 1947. For each, we retain 25 days actually observed and centered on the calendar month, which was the relative sunspot number maximum epoch. So, for instance, you see for the maximum of 1979, we have all the days, calendar days of September, past the first 9 days of October, to have a total of 25 observed days. The daily total number of spots on the solar disk found in this project from the data in the Council drawing archive is this, and the median is this. So all in all, for the mean number, we have a mean number of 127. We arrive at the median of 118 sunspots. This is a first approach. And this is a second approach in which now from the same data, this is excerpted for visibility on this board. We have in fact not only the cases from 98 sunspots to 138 sunspots here at the bottom, but for more, but for visibility we show on this board only this excerpt, in which you see that if you build a bin of 5 units for the number of sunspots, i.e. the n number of spots which will be in the center of this interval plus or minus 2, the mode now of the observations shown in the previous page will be 121, which is centered in this way. For these counts per day, there are 8 days observed, 8 occurrences. This is more than any other set of 5 numbers, 5 counts of spots. So this is the mode. And the secondary modes, which are not modes, but except this one would be the modes, they are at 101 and 136. So in the middle of the distribution, there is really no other value which is competing with 121. In this case, the mode is slightly higher than the median, which we found to be 118, and is much less than the average of 127. We now do a control of these results based solely on Council data. Using the data from the Sun network of the United States Air Force. This is a very good control versus results obtained from a single station, because Sun is the only array of solar stations which is spread over the entire globe and yet is centralized and calibrated by the US Air Force and NOAA. NOAA being the source of the results through this website. So in this case, we perform this control only for the maximum of cycle number 23. These are the almost 300 days in which number of sunspots was more than 100 at this maximum epoch according to the Sun data, and these are the days from 1999 to 2003 which are under review. And what we find in this case is that the peak number of days, which is 12, is found for a count of exactly 120 sunspots. You see that the count is rising from 100 to 120, and then it is falling sharply and will never again approach a number of at least 10 days. So as for the number of spots at the surface of the Sun on the disk, which is a hemisphere, and can be, by a rotation, translated into a number of sunspots per hemisphere, north versus south, is about 120 sunspots simultaneously. We can say simultaneously because we reported daily numbers of sunspots, but in fact they are found on drawings which were performed at a specific minute, in a matter of seconds, instead of being performed over a 24-hour interval. So these are not at all daily values, but instantaneous values. So these are numbers of simultaneous sunspots per hemisphere that seem to be characteristic from 118 to 100, maybe 23, with a central value which may be 120 exactly, but maybe as well perhaps say 121. Whether it is 121, 120 or 119 doesn't make a difference, because our goal is to assess a number of bipoles. We have to divide by 2 and get an integral number of bipoles, which in any case will be 60, or very, very close to 60. So this confirms the conjecture from part 1 that the 60 labs at the solar surface translate into 60 bipoles per hemisphere at the solar surface. At the time when the labs reach the count of 60, there are also 60 bipoles, at least according to the results shown here and from the select data that we arbitrarily chose. We now turn to the number of sunspot groups. Again, to approach the true number of physical sunspot groups, we turn to the Sun network data. Then we will check by control from still another source. We turn again to the peak of cycle 23 with almost 300 observed days, in which were seen 3 to 20 groups. We'll show in the next table the number of groups according to the number of days they were seen, from 0 to 20 groups. And we will find that there are 11 groups that was the median or the characteristic number of groups seen during the peak of cycle number 23. However, we will also see that the 11th group probably is not a physical one. The 11th largest sunspot group consisted in most days of 0 spots, and only in less than half of the days of 1 or 2 spots. And we want to have an actual group which must consist of at least 1 bipole, i.e. 2 sunspots. So this finding in the next page, which we will see now, corresponds in fact rather to arguably to 10 physical groups. You see, this is on this table the number of sunspot groups from 0 to 20, and the number of days on which the groups were seen. And on 47 days were seen 11 sunspot groups. You see how from 0 to 11 there is an increase and then a decrease from 11 to 20 groups. Of course, this is over a time span of almost 300 days, and we want to have the number of groups only over 1 rotation. So arguably, in fact, the number of groups over just 1 rotation, the peak rotation, would be even more than 11, but we do not have this data. We now compare with yet another control source, which is from secondary statistics now, as in all of the rest of the Fivefold Sun project. from 1875 to 2010, we find in the literature estimates of how many groups there were in the epoch of the sunspot number cycle peak. And we see from Hoyt and Eddy in 1982 the estimated value for the known cycles up to that time, which are given here. For instance, at the peak of the cycle in 1937, there were 10.2 groups that were seen at the solar surface. With an extension by Wilson in 2014, we can have the full series from 1875 to 2010. And we find that for the calendar year of the yearly maximum in the relative sunspot number, the median number of sunspot groups is 9.8, and the mean is more than 9.9 but less than 10. Hence, for the peak rotation, the number of groups must be at least 10, maybe is 11, maybe is 12, but we do not have this data. However, it is reasonable to suppose that it is slightly more than 10, and yet the physical number of groups would be only 10 if the 11th and perhaps the 12th largest sunspot group consisted statistically of less than one sunspot, but more than 0, a statistical fractional value, or also less than 2, which would not, from our point of view, compose a B-pole. So we remain with the value of a number for the peak rotation of the solar cycle of 10 sunspot groups, with possibly a statistical 11th group, which is not consisting of a B-pole. This is the end, ladies and gentlemen, of video 28. In the next video, we will go into the distribution of the numbers of sunspots per sunspot group, in which will be shown what was asserted already today, that there is a very sharp fall in the distribution of these numbers, so that for the 9th, 10th, and 11th sunspot groups, up to 20 of these groups may be seen simultaneously. In a statistical point of view, there is hardly more than one sunspot for groups that are in position after the 10th largest group. I thank you for your attention.